What is geometry? Well, according to Merriam-Webster, geometry is a branch of mathematics that deals with the measurement, properties, and relationships of points, lines, angles, surfaces, and solids. But I don't really think this is a good definition because it kind of just throws a bunch of vocab words at you and doesn't really explain to you what the nature of geometry actually is. And it brings up questions like, well, okay, what's a point? What's a line? And all of these questions are actually answered in this book called The Elements by a guy named Euclid. So Euclid was a very old, famous geometer that sought to answer these types of questions. And in his book, he laid out 5 postulates. According to the American Mathematical Monthly, these 5 postulates are: 1, a straight line may be drawn from any point to another point. 2, a finite straight line may be extended continuously in a straight line. 3, a circle may be described with any center and any radius. 4, all right angles are equal. And 5, through a given point, precisely one straight line can be drawn parallel to a given straight line. So on these postulates, all of geometry can actually be derived or built on. So any theorem you've ever heard, like the Pythagorean theorem or a volume formula, stuff like that, all of those are derived from just these postulates. And I think that's pretty impressive that something so simple, like these 5 postulates are pretty simple, but they can yield something so complex as geometry. So not everyone agreed with Euclid, though, that these are the 5 postulates. Some people thought that the 5th postulate was actually not self-evident. And you can kind of understand why they thought that, So, the first 4 postulates are about lines, circles, angles, and the 5th postulate is about the relationship between, if you have a line and you take a point and you can only draw one parallel line through that point to the first line. It's a little more complicated. It's a little more involved than the first 4 postulates. So according to Florence P. Lewis, a mathematician and astronomer, early mathematicians were skeptical on whether or not postulate 5 was self-evident at all. Now, they went about, there's 2 methods you can kind of go about to prove or disprove the validity of postulate 5. Method 1 would be, if you take the first 4 postulates and you use them to prove the 5th postulate, then that would mean that the 5th postulate, it doesn't deserve to be a postulate, it's not self-evident, and you need to prove it. The method 2 states that if you can take the 5th postulate and change it, so you make it a different type of statement on parallel lines, and then you recombine it with the first 4 postulates, well, if you are yielded a new, internally consistent but valid form of geometry, then that means that the 5th postulate is necessary and is a postulate for Euclidean geometry, because without it, you get a different type of geometry. But if you were to take the 5th postulate, change it, and not be able to combine it with the first 4, then that means it's not a postulate. There's something wrong, and it's not self-evident. Independently, a Russian mathematician and 2 Hungarian mathematicians, a father and son duo, they actually came up with hyperbolic geometry. And this is a type of geometry that uses method 2, and it says that we're going to keep the first 4 postulates the same, but we're going to change the nature of parallel lines or change the 5th postulate. So hyperbolic geometry can be pretty difficult to conceptualize, but I think with the aid of visuals, it's not that hard. So Euclidean space has no curve. It's a completely flat, and this is very easy to understand. It's just a piece of paper with a graph on it would be an accurate representation of 2-dimensional Euclidean space. But if you wanted to accurately represent 2-dimensional hyperbolic space, you would not be able to just use a flat piece of paper, because hyperbolic space, as you move from a point, hyperbolic space kind of expands quicker than Euclidean space. And I'm not using the exact correct terminology, but this gets the point across. And some plants in nature actually exhibit hyperbolic shaping. And you can kind of see how as these plants get more and more complicated and wavy, the surface area of their leaf is actually expanding very quickly compared to if it was just a flat disc. And this is what hyperbolic geometry is. Its surface area, it's much bigger, quicker than Euclidean geometry. So because hyperbolic geometry doesn't really fit onto a flat page normally, we can make some compromises when representing it on a flat page. We can do things like morph distance. A straight line is no longer the shortest distance between 2 points. And according to Ruth Berger, that's actually what a Poincaré disk is. So according to Berger, it's like a window into the hyperbolic dimension. And the center of a disk is kind of where things are biggest and most resolved. And as you move to the edge of the disk, things become, more and more distant quicker, and you can never reach the edge of a disk. The edge of a disk is a limit to infinity. So a Poincaré disk represents the entire hyperbolic dimension on a unit disk, and it does this by distorting distance and direction. So using a Poincaré disk and just a normal grid, we can compare hyperbolic space to Euclidean space and see how parallel lines act differently. So in Euclidean space, parallel lines work just as you would expect them to. If you're given a line AB and you're given a point C, you can only make one line that is parallel to AB through point C. But if we look at a Poincaré disk in hyperbolic space, we can actually see that if we're given a line AB that goes through the diameter of the disk, well, we can actually draw infinitely many lines through point C that are parallel to line AB. So after hearing this, you might be a little skeptical. You might think there's no way that those lines on the Poincaré disk are actually parallel to AB. I mean, they're curved, and they don't even go on forever. They just end at the end of the disk. So first off, those lines are not curved. We are using the Poincaré disk as a lens to look into the dimension of hyperbolic space. So those lines are not actually curved, they just look curved when we put them onto our little Poincaré disk lens. And they don't end at the end of the disk. As the edges of the disk get closer and closer, the space gets infinitely smaller and smaller, and lines get infinitely longer and longer over shorter and shorter distances, which means that there is no end of a Poincaré disk. There's no, you cannot reach the edge from inside of the disk. So these lines actually do go on to infinity. We see them as ending, but they do go on to infinity. Now, this can be a bit difficult to picture, but this is where some really interesting visualizations play an important role. So here's a picture of a Poincaré disk with some lines drawn on it, and as you can see, this kind of demonstrates how, at the middle, things are a little clearer, and then as you get closer and closer towards the edges, it looks like things kind of almost fractalize and get more and more complex. And I think it's from this complexity where a lot of the beauty of geometry could be seen. It's kind of crazy how just these 5 rules can create such a complex system. Apparently, I'm not the only one who thinks this, because according to Harold Scott MacDonald Coxeter, one of the most important 20th century geometers, after learning of the Poincaré disk, M.C. Escher made a famous series of paintings titled Circle Limit 1 through 4. M.C. Escher is a very famous tessellationist, an artist. His two-dimensional tessellations could be very complex, and as you see here, he plays around with different rotations and flips and shapes, and he combines them together to create one image, and the patterns he makes are very beautiful. But according to Coxeter, Escher was not learned in mathematics, and he simply created all of his tessellations from his deep understanding and intuition of geometry. So Escher was actually so talented that he was able to intuit hyperbolic geometry in a Poincaré disk. And he's able to produce some beautiful hyperbolic tessellations that lie on the Poincaré disk. So I hope now you can kind of see how, geometry is not just a bunch of lines on a piece of paper. It's actually the very fundamental rules we agree on of what is geometry. And now that we understand them better, we can kind of play around with these rules and create some really interesting visuals. And I guess the most beautiful thing about geometry is the simplicity of the postulates themselves. All of our understanding and formulas, even some M.C. Escher tessellations, can be built upon just these 5 postulates.